Good morning. Thank you for participating in today's presentation where we will be looking at granulating, agglomerating, and pelletizing. Please feel free to use your chat box with any questions you have, and I'll be glad to answer them at the end of this presentation. The language for various granulating processes may be confusing. So, first, let's start by understanding the definition for the various processes. Granulating and agglomerating means the accumulation of fine powdery particles to form larger units by sticking them together using binders, transforming the fine powders into a free-flowing dust or granule. Pelletizing is the process of compressing or molding a material into a shape of a pellet. Why granulate and agglomerate? These processes are used throughout many industries to transform difficult to handle powders and fines into larger, easy to handle granules having a strong matrix. A granule may contain many different components and requires strength to hold them together in the matrix so that its chemistry remains intact after creating. There are many different reasons to granulate materials. Also, the requirements for granulating varies with each industry and application. For instance, recycling products, the size and shape of the granules are not very important. On the other hand, for high quality products like ceramic proppants, the size and roundness, and furthermore, the yields are very important. In this presentation, I'll provide an insight into granule design and different processing methods. Why do we want to granulate and what are the benefits? Well, some of the benefits: conditioning toxic particulate matter into a dust-free product, improve product flowability, improve product performance, improve storage and transport properties, prevent demixing effects during handling, yield higher bulk densities and less volume, produce a product in a defined shape, and control bulk densities. You can find agglomerates or granules everywhere, not only in industrial applications, but also at home, such as medicine tablets, washing powders, cold briquettes, fertilizer, cat litter, etc. All these products are distinctive in their own way, but they all follow the same physical laws of granulation. Today we'll review formation methods, granule design, and special granulating processes. Press agglomeration. Press agglomeration is the process of forming shapes using external forces. Some common processes include briquetting, which is a compaction technique where the feed material is pushed into the nip of two counter-rotating wheels. High pressure is applied and the rotating wheels compress the feed between the pockets to form shapes. Tablet or hydraulic pressing is a mechanical device that compresses powder into tablets. To form a tablet, the feed material is metered into a cavity where force is applied to fuse the material together. Extrusion. It's important to note that while the terms are often used interchangeably, pelletizing is distinctively different from pelletizing. Pelleting typically refers to the extrusion process where cylindrical pellets are formed by forcing material through a die and cut into pieces of a specific length. Granules can be produced by various mechanical granulating processes. This could be spray dry agglomeration, drum granulation, pan granulation, and mixed granulation. Spray dry agglomeration. Spray dry agglomeration, also referred to as wet agglomeration, involves the atomization of a liquid feed into very fine, small droplets with a hot drying gas, leading to flash drying of the droplets into solid particles. The particles are then separated from the drying gas using a cyclone or filter bag as a final spray dried product. So as you can see in the schematic here, atomized slurry is sprayed, heat gases flowing up, flash drying the product, and the finished or granules fall to the bottom of the chamber. As the water evaporates in the spray dried particles, they stick together to form a solid matrix, creating a granule with a hard shell. The granule size produced in spray dryers is usually less than 100 micron. The structure of these granules resembles a donut, as shown in Figure 1. This occurs when there is a high moisture or binder content. Additional slurry coating fills these cavities and increases the granule size. Figure 2. If the binder level is too high, the evaporation pressure inside the granule increases until it explodes, producing a hollow shell. This may affect the preceding process, causing defects in the final product. Build-up agglomeration. We will look at the three most common processes. To form a granule, fine particles need to be moistened with binder, forming a liquid bridge, allowing the particles to stick together. The final product resembles a blackberry structure. The blackberry structure is a cluster of fine granules combined to form a larger agglomerate. The best granulating results are found when the fineness of the starting powder is 150 mesh or smaller. Rule of thumb, the starting moisture for granulation should be approximately 13%. Here is a close-up view of the granule blackberry structure. Build-up agglomeration consists of dry mixing of powders, adding moisture and thoroughly coating the dry particles. The particles become sticky, forming a capillary bond, and the granulation process begins. With additional processing, there is a separation of the smaller satellite particles, yielding the desired shape. A final rolling of the granules rounds off any sharp edges, yielding a nice sphere. Starting with a wide particle size distribution in a mix results in the larger particles attaching themselves to the surface of a formed granule. These granules eventually fall off and possibly affecting the chemistry of the granule. For the best results, all the starting powder should be close in particle size. Granulating involves tumbling fine materials against each other in the presence of a binding agent. The binder causes the fines to become tacky and stick together. As they continue to tumble, they pick up more and more fines, a phenomenon referred to as coalescence. To form granules in rotating drums or pans, the powders and binders commonly need to be preconditioned in a mixer. Pelletizing drums are inclined cylindrical containers that rotate around their axis. The feed material is added at one end of the drum, and liquid is added via spray nozzles. As the drum rotates, friction between the material and drum wall transports the material upward, and at a certain point, the material rolls back. The tumbling action within the drum causes the material to pick up more fines and grow by coalescence. The speed of the drum is set so the rolling process can take place, resulting in the production of pellets. Drums do not display size separation and thus deliver a wide pellet size distribution. The product leaving the drum is screened, removing the overs and fines, which will be crushed and recirculated back into the system. Recirculating quantities are many times larger than the original feed amount. Pelletizing drums always run in a continuous mode. In the drum granulator, preconditioned or virgin material is fed into one end of the drum. Liquid binder is sprayed onto the material and the granulation process begins. Adjusting the liquid addition and rate of the rotational speed of the drum affects agitation and residence time, which will determine the final granule size. Energy input into the product is accomplished by material tumbling onto itself. For this reason, there are large differences in particle size distribution and density at the drum discharge. A roller screen is usually attached on the drum exit to separate pellets within the desired range, screening out the oversized and undersized material. The recirculating load tends to be approximately 150 to 250% by weight of feed. Disc pelletizers. Disc pelletizers are inclined containers with a cylindrical shape that rotates around its inclined axis. The fine material is continuously added and transported up the rotating disc until it falls back to the bottom due to the effects of gravity. The kidney-shaped circulation is formed where the rolling action grows the pellets in conjunction with the addition of a liquid spray. By adjusting the inclination and rotational speed of the disc, it is possible to vary the pellet size within wide limits, ranging from 1 millimeter to 30 millimeter. The granulating principle in the disc pelletizer is similar to the rotating drum. The granulation process begins in the upper quadrant of the disc, shown in zone 1, where the pellet and nuclei are rotating and begin to form. As the granules grow, they start migrating downwards towards zone 2. In zone 3, you start to notice a defined circulation of the granules until they reach a size and tumble off the edge of the disc, as shown in zone 4. The circulation area, zone 3, is called the granulation kidney due to its noticeable shape. Within this area, the rotational speed of the disc and additional moisture can be adjusted to achieve the target granule size. Stabilizing the process may require multiple steps, such as adjusting the feed rate into the disc, adjusting the disc angle, changing the location of material feed input, adjusting the rotational speed of the disc. In most cases, the raw material feed into the disc pelletizer has to be preconditioned in a mixer. Here is a slide showing a preconditioned powder prior to feed into the granulating drum or disc, and also the final product coming out. Disc pelletizers can get quite large, with disc diameters up to 25 foot in diameter. Disc pelletizers alone are not recognized for high efficiency. Therefore, in some cases, multiple units are required to achieve the required throughput rates. To ensure the product coming off the disc remains consistent and uniform, the pelletizing process requires monitoring at regular intervals. This monitoring is necessary because even minor fluctuations in the amounts of solids or liquids can alter the process. Effective applications for disc pelletizers include pellet or granule sizes up to 30 millimeters in diameter, having fragile products with little strength, products with high amount of coarse particles, particles with a wide size distribution, improving sphericity, making rounder granules and shapes. The granulating mixer. The granulating mixer has a rotating mixing pan and an eccentrically mounted mixing tool, also referred to as the rotor. By intense mixing, the particles are bound closely together with the addition of a binder. Once the nuclei of the granules have developed, the rotor speed is reduced. This is where the actual buildup agglomeration process begins to take place. The particle distribution can be controlled in a defined manner. Depending on the type of material being processed, granules up to 6 millimeter in diameter can be produced. This process can be fully automatic and run without supervision. Granulating in the rotating pan mixer can be batch or a continuous process. The Eirich mix granulator, you can achieve higher strength granules compared to preparing in a drum or disc. The Eirich mix granulator has three unique operating principles, including a rotating tool, or the rotor, a rotating mixing pan, a stationary multi-purpose tool, which also acts as a wall and bottom scraper, keeping the insides of the mixer clean. The rotating mixing pan. This is used to deliver the product into the high-speed agitator or rotor where energy is input into the product. The rotating tool or agitator can rotate in a clockwise or counterclockwise direction and also can vary its speed required depending on the energy you want to input into the product. The stationary multi-purpose tool produces a vertical component in the material current, cleans the pan wall and floor, and accelerates the discharge of the product inside the mixer. So as the product's coming around and passes through the rotor, the scraper pulls the material off the sidewall and delivers it right back into the agitator. So after one complete revolution of this mixing pan, you have a well-mixed product at that point. Another unique feature of the Eirich mix granulator is its inclined mixing pan, typically set at 20 or 30 degrees. As the pan rotates, the material is pulled off the bottom and we let gravity work for us. The product gets to 11, 12 o'clock position and rolls over. So everything within that mixing container becomes active, providing a vertical and horizontal mixing action. Today's Eirich mix granulator was designed with the disc pelletizer in mind. Eirich already had a rotating pan mixer dating back to the early 1900s, but in the early 70s, the R-type mixer with an inclined mixing pan was introduced, mimicking the disc pelletizer. Mixing and granulating in a single machine simplifies production process by eliminating additional processing equipment. The Eirich intensive mix granulator is extremely efficient at dry mixing, granulating, coating, and preparing plastic bodies for extrusion. The Eirich mix granulator is excellent at granulating, but also we can take filter cake or sludges, and by mixing in dry powders can create granules. We already touched on how a granule is formed, but when additional processing steps such as coating or rounding off the particles are required, sequential processing steps such as re-wetting and adding dry powders into the mix to shape the granules can be employed to achieve the desired results. Starting with the blackberry structure formed by the blackberry structure, powdering the powders, providing nice round surfaces on the finished granules. To form a granule in the Eirich mixer, the following steps are required. Dry mixing, moistening. After moistening, the particles get sticky and begin forming a bond. The granule is densified with the impact energy of the rotor, and the granules begin to grow, shaping the granule to a desired shape. The Eirich mixers offers the versatility of creating microgranules up to a granule size of 6 millimeters in diameter. Here is a video demonstration of the granulation and coating process in the Eirich mixer. The mixer that we're showing here is a 150 liter capacity machine. We're going to be processing some alumina powders and granulating with water. We're going to put all the raw materials into the mixer at one time and go through a dry mixing phase. Here we're adding an iron oxide just to show how quickly the material gets distributed into the mass of the material. And adding water as the binding agent. The intensity of the tool densifies the product, coating all the granules, and you start seeing the powders transforming into granules. After a short mixing time, you have 1 millimeter granules. By the addition of water or moisture, we can grow the granules larger, and additional processing or mixing time, the granules get larger also. So here you'll see the three phases and time from small granules, and with time the granule size increases. So we can also coat by adding a dry powder. Now that we created the granules, we add a dry powder to coat the particles, and this can be useful for removing surface tension or moisture off the granule to make a nice free flowable product after coming out of the mixer. Now, the coating can be a dry powder as shown, or there can be liquid coatings applied also. And you'll notice that the granules were coated without breaking up the original granules. So the mixer is intense enough, puts enough energy into the product to densify a product, yet keeping the integrity of the granule. It's difficult to control the granulation process if you cannot input the proper energy into the product while processing. In this slide, you can see that a certain distribution can be stable and the granules grow at the same rate, the pink and blue line. Lowering the energy input with a slower speed and extending the mixing time, the granules will grow and the particle distribution will get wider, as shown in the yellow line. If the rotor speed is too slow or moisture too high, the larger particles grow quicker. A huge advantage of the Eirich mixer is its ability to control the particle size by adjusting the rotor speed. Also, if the particle gets too large, the rotor speed can be increased and the granules resized. This slide shows that running at higher rotor speeds or energy input will influence the particle growth and tighten the distribution curve. So starting at 400 RPM, when we increase the speed up to 800 RPM, the distribution gets much tighter. Longer granulating times will lead to a coarser product. Like a snowball rolling down a hill, the longer you roll the granule, the larger it becomes. The additional rolling picks up any loose fines and attaches itself to the larger granules. Here is an example of granulating material to produce ceramic proppants. The higher tool speeds enables the particle size distribution curve to stay very tight and narrow. The granulation process can also be carried out in steps. Some applications require higher initial speeds to disperse liquids and then slowed to grow the granules and round off, improving sphericity. The Eirich rotating pan mixer allows you this processing flexibility. You will never achieve 100% yields within a specific distribution. The oversized material needs to be screened, dried, and crushed before being put back into the system. Using an Eirich optimizer reduces the amount of product that has to be recirculated. We found that by implementing the optimizer, we are able to increase yields within a target range up to 90% of usable product. The operating principle of the Eirich optimizer is two counter current rotating discs running at high speeds with an adjustable gap between the two discs. The gap defines the maximum limit of particles leaving the machine. Here is an example before and after stabilizing a granulated material in the Eirich optimizer. Product material coming out of the mixer, we were seeing yields of 65%. Processing the materials through the optimizer, we increased the yields up to 90%. Now you see a nice product without any large agglomerates and uniform properties. This graph shows a distribution curve where the target particle size had to fall between the red and blue lines. The green line indicates the product coming out of the mixer, and the blue line indicates the particle size after standardization. The previous slides explained the versatility and processing advantages of the Eirich mixed granulator. Here is a summary. Homogeneous mixing of numerous ingredients in batch operation. Perfect wetting with liquids, binders by fast running rotor tool. Turn powders into granules. Turning pastes and filter cakes into granules. Coating granules with solids or liquids. Tightening the size distribution. Producing smaller granules, 0.5 millimeter to 6 millimeter, with high yield possibilities, working in conjunction with pelletizing discs or drums. In a typical granulating system, we would take the raw material, feed to an Eirich mixed granulator, granulate, dry, and screen the final product. So here you'll see all the raw materials being batched into the rotating pan mixer. Granules are formed, leaving the mixer, going through the drying and screening process. The Eirich mixer can also be used to precondition the raw feed and provide a continuous feed to a pelletizing drum. So here we're taking the raw materials, preconditioning, adding the moisture, combining all the dries, and feeding to a pelletizing drum. Eirich also offers a continuous mixer for preconditioning feed to downstream equipment. There can be a range of reasons for choosing combined methods. If the application presents special demands in terms of grain roundness, then the granules can be manufactured in combination with a mixing disc pelletizer. To accomplish this, the granules are produced in the mixer and then used as pellet feed. The pre-granulated pellet already has the correct moisture and instantly starts rolling into the required shape in the disc pelletizer, thereby significantly accelerating the pellet formation. The combination of mixer and disc pelletizer is also recommended for sensitive materials in which an equilibrium is established in the mixer and ready for additional formation. Here we see batch mixing, preparing materials, feeding into a table feeder, and then feeding disc pelletizers. So we're preconditioning the raw materials, wetting of the mix and recycled product, dosing the wetted powder via table feeder into the disc pelletizers, and creating pellets. Afterwards, screening, crushing of dry oversized material, and returning back into the system. So in the granulation process, there's always a recirculation loop where the overs and fines are recirculated back into the system. When preparing granules in a batch process, an intermediate device such as an Eirich table feeder can be implemented, providing a continuous feed to downstream equipment. So in the batch process, that gives us the best control of our process. So we would prepare granules by batch and discharge into the hopper of a table feeder. This device would take the materials and feed on a continuous basis to downstream equipment. The Eirich table feeder consists of a transition hopper rotating table, and adjustable discharge blade. The flat rotating table has vertical pins that gently funnel material from the hopper cone to the discharge blade. As the table rotates, the vertical pins agitate the material and keep it flowing evenly into the discharge blade. The discharge rate is adjustable by changing the angle of the discharge blade or the table rotational speed. The internal wall scraper in the table feeder prevents material buildup on the sidewalls, ensuring consistent flow. Moisture. The hollow spaces between the granules should be approximately 90 to 95%, resulting in the strongest pellets. Coating each grain by driving the moisture to the surface of the granule requires energy. The strongest pellets are formed when capillary bonds are achieved, increasing the surface tension of the granules. So as you can see in the slide over here, we have the liquid droplets, and what we're trying to accomplish is coating each individual grain and having them stick together to form the granules. This requires densification and energy to bring the moisture to the surface of the granule. This graph shows that sometimes it takes time and energy densifying powders before the granulation process starts. Here we ran the mixer at a slow speed for 12 minutes. At that point, the granulation process begins. Moisture gets trapped in the hollow pores between the small granules, and by introducing energy, densifies the material, filling the hollow pores between the granules and driving the moisture to the surface. And that's when the granulation process starts. So a lot of times you will not see the granulation process start as soon as you add water, but with physical energy driven into the particles, bringing the moisture to the surface of the granule formation can begin. Stabilizing. Product stability is the state of being firmly fixed or not likely to move or change. The binder used in the process has considerable influence on the formation and stability of the final product. Physical binder effects influence high grain strengths, high stabilities after drying, high porosity, low or no porosity, favorable dispersion. Chemical effects could include product remaining in the product as a pressing agent, stabilization prior to drying or sintering, residue-free burnout, reduction of off gases during drying. In most cases, some type of binder has to be used in the granulation process. The binder can be something simple as water, or as an example, some of the organic and inorganic binders as shown on this slide. So inorganic binders can include bentonite, cement, silicas, plasters, clays, organic binders, carbamethylcellulose, CMC molasses, pitch or tar resin, starch, polyvinyl alcohol, and obviously a number of other binders that would be compatible with your process. The stability of a granule is achieved when the product is easily wettable and can absorb moisture. Selection of an appropriate binder, particle distribution. Particles having the same shape, such as a perfect sphere or cube, are difficult to agglomerate. Particles with a coarse surface granulate more effectively. In some cases, the created granules require additional processing. For instance, ceramic proppants or iron pellets are sintered. Sintering occurs when the moisture is removed from the mass by applying high temperatures, usually in a rotary kiln. The powdered materials coalesce into a solid mass. The high temperatures melt the grains together. This melting happens in several steps until a strong matrix is produced. Thermal drying. Drying the surface, drying the Drying the surface of the granule with heat or coating the granule with dry dust reduces the surface tension of the granule, making it less sticky and easy to handle. Improving the flowability of the finished granule could be achieved by thermally removing the surface moisture of the granule or dusting powder with dry dust. And this will all be done as the granules being processed in the rotating pan mixer. There are many ways to dry. Convection drying can be used by blowing heated air into the mixer after the granule is created, hardening or curing the surface of the granule. When granulating products with solvents, we would use a vacuum drying system, heating the product, possibly with steam, removing the moisture by condensing the liquids, and initiating the product granulation. So this would be a complete closed loop system. The onion skin structure with thermal drying is achieved by creating the granule and adding additional powder or moisture, forming a shell around the nuclei. The process can be repeated to create the desired structure. Common applications, for example, are time-released products similar to a fertilizer. The onion skin structure can also be accomplished without thermal drying by moistening the surface of the granule and coating with the dry powder to create the desired product. This process can be repeated to create the desired structure and size. Instantizing. Instantizing is a technique that improves the dispersibility and solubility of powders introduced to a liquid. The instantizing process uses steam to produce granules that are easily dissolved in liquid. Here's a photo of an instantized coated granule. Melt agglomeration. Melt agglomeration is the process of melting a binder, for instance, a wax, outside of the mixer, heating the dry powder and adding the liquid wax onto the powder, creating a granule. The melt agglomeration process, after addition of the binder, the product will turn into a stiff mass. The energy of the rotor tool will break apart this mass and turn the product into fine granules as seen in the last slide here. Thank you for participating in today's presentation. I trust you found it informative. If you should have any immediate questions, please submit your questions in the chat box and I'll be glad to answer. If you need to address any applications in detail or require additional information, please do not hesitate to visit our website or call me direct. Thank you very much.
Thank you, Nick, for this great presentation. We do have a few questions, so I'm gonna read them to you. The first one is from John. He's asking, how small can you make granules in an Eirich mixer? What is the lower effective size?
Well, the smallest size is going to depend on the starting materials. So the finer the starting material, the smaller you can grow a granule. As we mentioned, the granulation process is taking a bunch of fine granules to make a blackberry type structure. So you're going to need to glue half a dozen to a dozen of these fine particles together. So what we see is we can get granules in the 100 micron range, depending on the fineness of the granules, the starting powders, I should say.
Okay, then Robert is asking, what is yield without optimizer?
In the best case scenario, you're going to see approximately 65 to 70% yield under perfect conditions. You're never going to get 100%. So typically you are going to be recycling 30% of the product. And that's all going to depend on your distribution range. The wider the distribution, the less you're going to be recycling.
Okay. Third question, can we send a small quantity of sample to test in your pelletizer coating machines?
Yes, we have our test center, which is located in Gurnee, Illinois. We encourage you to send your product to us. We offer free feasibility trials in our smaller mixers. Once we process your material and you feel it's effective with your process or application, we can schedule you for further trials or for a full day trial, mixing larger batches and optimizing your process.
These questions are coming in here. Let's see, we have one more here. What binders are useful for agglomerating biochar powder to round particles 2 to 3 millimeter in size?
Biochar particles. Well, it all depends on what the granule is going to be used for. Does it need to be dissolved? Is there a specific hardness that you're looking for? So the binders all play a factor into what you're trying to accomplish in the final product. So biochar products, as I mentioned, as long as the particle size is 150 mesh or finer, there is an organic or inorganic binder out there to granulate that product.
Okay. Other question, does water affect the formula of the customers when it comes to pelletizing?
Can you repeat that, Lena?
Does water affect the formula of the customers? Talking about pelletizing.
Well, water is used in a lot of applications as the binder itself. As long as the product that we're granulating is reactive, the water certainly can be used as a binder. Again, the starting moisture, typically you're going to require about 13%. If the particle size is very fine, that means you have a higher surface area of the particles, so more water or binder would be required for the finer particles.
Okay. Next question. Is there more information on pelletizing?
Yes, this was the condensed version. We had a 40-minute time window here. Absolutely, there is more information. Please, you can contact Eirich Machines, myself, with any questions you may have regarding pelletizing, and we'd be glad to provide you with additional information.
Great. Oh, let's see. One more question here. I want 3 pounds to 6 pounds force crush strength for a biochar 2 to 3 millimeter granule. What is good binder to use?
For the biochar, did we have this question already?
Yeah, maybe we can also send personal answers to these questions in emails. We have the contact information.
Yes, whoever, what we need to know are the specifics, granule size and hardness, the stability as we discussed, granule size, stability, then we can recommend a binder for you. We're not chemists by any means, but there are the common binders which I had on one of the slides there that we use quite commonly. It can be organic, inorganic, starches, clays. So it's all dependent on what our clients are looking for as a final product quality. And I'm sure we can find the right solution or process to deliver that product.
Okay. And last question here. We've been asked if we can send this recording in email, and yes, we can do that. We'll do that in a few days. We'll send you a link to this recording so you can see it again. Look at it again. Okay, that was all the questions, Nick.
Thank you very much.